The geometric mean in right triangles. Similarities in right triangles. In our warm-up, we're going to see a problem that we were working on the other day, which was the side splitter theorem problem. Given a triangle with a line parallel to one of the sides of the triangle, here we say have two parallel lines, splits the two sides into two pieces that will be proportional to the other side split up into the two pieces. Proportional means we can use a proportion to solve this. So you'll see I have on one side the two parts, x and x plus 12. X over x plus 12 is the first ratio. And then the two other parts would be 11 and would be 22. Since 33 minus 11 is 22. Setting up a proportion means that we then can solve it through cross multiplying. But first, sometimes we can take a fraction and reduce it down. So here we have 11 over 22 equals 1/2. Now, as we cross multiply, 2 times x equals 1 times x plus 12. Alright, so that's the cross multiplying. We can collect like terms and solve for x. X equals 12. The geometric mean is when the means of a proportion are the same number. That the number is called the geometric mean of the extreme. So let's take a look at what this actually means. So in the proportion, we notice that two pieces, which we call the mean, here x, those things are the same number, the same variable. So when that happens in a proportion, we call this the geometric mean of the two other numbers in there, a and b. And if you cross multiply and solve that proportion, you get that x, the geometric mean, is the square root of the product of those two numbers. So for instance, if we have the two numbers 9 and 4, the geometric mean would be the square root of their product. Since 9 times 4 is 36, the square root of 36 is 6. A few examples. So we have 5 and 45, and we'd like to find the geometric mean between the two of them. So we place 5 and 45 diagonally in the proportion, and we set the geometric mean equal to x, and we represent that two places in the proportion, one on top and one on the bottom, on either side of the equal sign. By cross multiplying, we get 5 times 45 equals x times x, or x squared. To solve something with an x squared in it, you often have to take the square root. So we take the square root of both sides. The square root will cancel the square and just give us x on the right-hand side. And in order to evaluate the square root on the left, I have to look for perfect squares inside the radical. And with a little bit of factoring and rearranging, I find that we have two perfect squares under the radical, 25, as well as 9. And the product of a radical is the product of, let me say that again, the radical of a product is the product of the radicals. So separately, 5 times 3, which is the square root of 5 and the square root of 9, equals 15. We'll do this again for 12 and 15. We place 12 and 15 on the top and the bottom of the different ratios respectively, and x being our geometric mean, the thing that is the same in both proportions, both ratios in the proportion, we set one on top and one on the bottom. When we cross multiply this situation, again we're going to get x squared equals the product of 12 times 12 times 15. The square root on the right hand side just gives us x, and now we have to evaluate the square root on the left. 12 can be factored into 4 times 3, and 15 into 3 times 5. Since 3 times 3 is 9, a perfect square, we can put those back together and find perfect squares underneath the square root. Both 4 and 9 are perfect squares, but 5 is not. So we can split up the radical into their separate radicals and evaluate the perfect square parts. Square root of 4 is 2, square root of 9 is 3, square root of 5 has to stay the square root of 5. So 2 times 3 being 6, x equals 6 square root of 5. You're going to see sometimes radicals will be in the answers with these types of problems frequently. Okay, so now we're going to take a look at right triangles inside a bigger right triangle and show how they are similar. So when we drop an altitude from a right triangle to its hypotenuse, we get two smaller right triangles inside. And comparing the lengths of their sides, they are proportional. So for the big right triangle ABC and one of the smaller right triangles ADC, we can show by comparing their angles, which would be congruent to each other, which sides would correspond. There's going to be three proportions we set up for two triangles. Since the triangles have three sides, we can do three ratios. So matching corresponding parts is the name of the game. B corresponds with x, so we're going to make a ratio of b over x. Matching the next side, let's see that A matches with H. And again, the reason that they correspond is because they're across from the same marked angle. So we do A over H, and the third set of corresponding sides would be C and B. C over B. So we've set up a bunch of ratios, or two proportions, or three proportions actually, with the sides of the triangles. Next, we're going to compare the two small triangles that are inside the big triangle, so ADC and CDB. Alright, and since their angles are marked correspondingly, we can match their sides correspondingly. Setting up three proportions again for these two triangles. We note side X is proportional to H in the respect that those are corresponding sides. So we put X over H. That'll be equal to H over Y and B over A. Lastly, we can compare triangle CBD to the big triangle ABC. Alright, so we'll do that part next. So now ABC and CBD are being compared. We set up the three proportions for them. Correspondingly, B goes with H, so we make a fraction with that. Next is side A corresponds with side Y, so we make the ratio A over Y. And C over A. So we're going to see here now, in these sets of ratios, we're going to be able to find a proportion with a geometric mean. Remember, a geometric mean is a number that shows up, in a sense, twice in a proportion. One on one side of the equation and one on the other side of the equation. So now, for each one of these sets, we're going to find where the geometric mean proportion is. And this will help us solve some problems with right triangles. So in the first set, notice that B is the shared piece here amongst these two ratios, these two fractions. So we have the proportion B over X is equal to C over B. The geometric mean here is B. In comparing the two small inside triangles, we see that H, which is known as the altitude, is the geometric mean in this case. So we can take the two fractions with the same letter, the same variable, and put them together. Last but not least, we find the two ratios with the same pieces and we set them equal to each other, and the piece that is the same, the A in this case, would be called the geometric mean for that proportion. Now these ratios and proportions that we can find correspond to rules that we can call one the altitude rule and the other two the leg rules. So the one that's in the middle there, we're going to call that the altitude rule, and the ones that are on the sides there, they'll be the leg rules. We're going to explore why the two ones are called leg rule and why the one in the middle is called the altitude rule. I mean, essentially, when we start setting up the diagram, we're going to see that this corresponds to finding the corresponding parts that we are given in a problem. So what you see me doing here is solving the proportions by cross-multiplying them and solving for the geometric mean. So in the first one I solved for B, the second one I solved for H, and the third one I'm solving for A, noting that I'm having to take the square root. Alright, so this is in practice what you're going to have to do to solve some of these problems. Let's take a look at a few examples. So the altitude rule can be summarized as this. If one of the pieces of the problem that we're given is the altitude, and the other parts are the pieces of the hypotenuse that are broken up by the altitude there, then we can see that when I highlight that situation, it kind of looks like the perpendicular symbol, or an upside down T. So when we have those particular pieces, we can set up the altitude rule where we have the altitude h as the geometric mean, and the other two parts of the hypotenuse are the two numbers that fit into the other parts of the proportion. This is a very useful rule. So this would be demonstrated if we have E is the hypotenuse, if E is the altitude and AB are the two parts of the hypotenuse. E is the thing that shows up twice in the proportion, and the parts of the hypotenuse A and B fill in the other spots. If we let the altitude be x, then the x would be the thing that shows up twice. So when we cross multiply, we get x squared equals a times b, and taking the square root of both sides gives us x equals the square root of whatever a times b is. This is known as the altitude rule, and because the word altitude has the letter T in it, we think about that upside down perpendicular symbol as an upside down T. It kind of reminds us that when we see that pattern in the triangle, to use the altitude rule, the altitude being the geometric mean. So here the altitude is x and it shows up in our problem, so we know that's going to show up twice in our proportion. It is the geometric mean. So when we know which part is the geometric mean, since this the altitude is the altitude rule, put it twice. The other two parts, which are 4 and 12, will be filling into the rest of the proportion. So it really doesn't matter which one you put on the top and which one you put on the bottom. Once we cross multiply, it'll work out to the same equation. X squared equals 4 times 12. And taking the square root of both sides, we actually can factor 12 into 4 times 3 and get a perfect square out of that. So 4 radical 3 winds up being the simplified answer. In the next problem, again, we see the altitude rule by highlighting the parts we have that upside down T pattern. The altitude is x, and the other parts are 3 and 15. I'm going to cross multiply these. This time I'll multiply 3 and 15 together to get 45. If you do it that way, it's fine. But then you have to try to reduce that down, so we factor it into 9 times 5, and we get 3 radical 5 as the answer. Next is the leg rule. So the legs of the big right triangle are on the outside. They are not the hypotenuse. So they connect to the right angle. Now often the pieces that are the parts of the hypotenuse are called projections, but what I'm going to focus on here is this L pattern, either a backwards L or a forwards looking L. Alright, so what we're really going to be doing is comparing the big right triangle ABC from the beginning and one of the smaller right triangles inside. Not both small triangles inside, either one or the other. So it depends on what pieces of the problem we're given, and in this case, we don't know anything about the altitude, so the altitude rule is out. So either we'll be working with the small little triangle on the left here and highlighted in yellow and the big one in green, right? Or not including those other pieces I just took away here. Right, so we may have those pieces of information, or we may have the other small right triangle inside there, the leg and the projection known, and then we can compare that to the big right triangle, which shares the leg and part of the hypotenuse. So the part that they both share, the big triangle and the small little triangle, is the leg part, and that's why we call this the leg rule. So since they both share the side that's called the leg, the big right triangle and the smaller one inside, that's the geometric mean. It's the thing that shows up twice in the proportion. So if we concentrate on the little right triangle on the left here, and I'm highlighting that in green, and then the big right triangle and I'm highlighting in yellow, then I can put those pieces together. So the two pieces that they share here is the side C, so that would show up twice in the proportion. Then I would use the small little piece of the right triangle that I didn't use in green, so that would be the side B, and the hypotenuse. So B and whatever the hypotenuse is. I could have also put the hypotenuse down here and the part B up there. Again, it doesn't matter where I put those other two numbers, as long as I have the geometric mean, one on top and one on the bottom in the different fractions. If we're using the backwards L leg rule, okay, we have the other small little right triangle there highlighted in yellow, and the big right triangle parts highlighted in blue. The side that they share is side D here, so we're going to put D twice in the proportion. Side A and the hypotenuse side are the parts that go into the other slots in the proportion. And once again, we could swap those in their order, put the hypotenuse part at the bottom there and the A on the top, and it wouldn't matter. Once you cross multiply, you get the same answer. So the geometric means are the things that are the same that show up twice in the proportion, which I've highlighted here in purple, and that would be when they form this L pattern, we call it the leg rule. The leg, L, whichever part of the L is the leg, that's the geometric mean. So let's apply this in example 2. Solve for x. Notice that x is the leg and not the altitude here. The altitude is not marked, so we're not using the altitude rule. So it's the outside left part of the big right triangle. X is the leg. And so we're going to be dealing with that small right triangle inside in the left-hand part, highlighted in purple here, and the big right triangle here. Now the big right triangle and the small right triangle both share the leg x, so that's our geometric mean. The small right triangle has a side of 5. I'll place that in one of the slots. And the big right triangle has a hypotenuse highlighted here, which is 5 plus 15, or 20. We'll put that in the second slot there. Okay, again, so to solve a proportion, we cross multiply. It's sort of like bringing the denominators upstairs across the equal sign. So x times x is x squared. 5 times 20 is 100. And 100 is actually a perfect square. So when we simplify this, we won't have a radical left over in our answer. Sometimes we won't, sometimes we do. Depends on if we get a perfect square. X is equal to 10. Okay, finding the length BD, I'm going to mark that as X in my diagram here. Okay, so BD, X. And what I'm going to notice is that the altitude, again, is not given here or marked, so I'm not using the altitude rule. This is the backwards leg rule, meaning just the L is backwards. So the small little right triangle inside has 6 and X as its sides. The big right triangle has its sides 6 and, well, the hypotenuse would be a combination of X and 5. So X plus 5 would be the hypotenuse. Okay, so X would fill in one spot, but then the hypotenuse there has to be a combination of 5 and X. So we could say 5 plus X, or what I like is X plus 5. So in the other spot, I put X plus 5. Careful when cross multiplying, we have a binomial here. We have to use the distributive property. So when I multiply 6 times 6, it's 36, but when I multiply x times x plus 5, that's x squared plus 5x. This is a quadratic equation because of the x squared term, so we're going to bring everything to one side, and we want that x squared term to remain positive, so I'll bring the 36 to the other side by subtracting. And from algebra, you remember, solving a quadratic equation requires us to factor it. Two numbers that multiply to negative 36 but add to positive 5. 4 and 9 both multiply 36, and when I add positive 9 and negative 4, I get positive 5. So that the factor x minus 4 and x plus 9 will be our factors. And when we set each of these factors equal to 0 and solve for x, we get 2 answers for every quadratic equation. So in this case, we get positive 4 and negative 9. Now remembering that x represents a length of a triangle side, I have to know that this negative 9 answer is no good. So x equals 4 can only be the answer here. We can only have positive lengths. All right, so what we would say is that x equals negative 9 is something we're going to reject. And that's in the context of this problem. If we were solving a quadratic equation in general and x didn't represent a length of anything, it was just a number, we could take both solutions. But in this case, it represents something. So here on the bottom I have a summary of the two rules, the altitude rule and the leg rule. And we're going to try this challenge problem here. Solve for x. Well, since the altitude is not being used here and the leg is involved, x plus 2 is the leg, that means that we're going to use the leg rule. Okay, so when we start setting up the leg rule, sometimes the right triangle might not be oriented in the way that you saw it in the example, so you just have to think about seeing the pattern. So here if I highlight the leg, x plus 2, and the small triangle that is connected to that, it has a side of x. Okay, and the big right triangle has a side x plus 2 as well, and its hypotenuse is x plus 5. Alright, so we're going to put x plus 2, the geometric mean here, twice in our proportion, one on top, one on the bottom. And then we're going to put the two parts of our big and small triangles. We have x and x plus 5. Careful with cross multiplying. Now we have a binomial multiplied with another binomial, as well as a monomial times a binomial. In other words, we have a lot of distributing to do. X times x is x squared, x times 2x is 2x, and I'm just going through and doing the distributive property here, so you get the idea. I'm going to clean up some common terms by adding them together. I'm going to try and collect like terms all on one side, so I'll subtract the x squared to the other side, and those actually disappear. Collecting the x's together, I'm going to subtract 4x to the other side, and wind up with x equals 4. So, our answer of x equals 4 can be substituted in, but this is the solution to our problem. Good luck with those homework problems.